In this video, students were going to discuss regarding pattern multiplication, how to get the radiation pattern without using ordinary techniques, directly how to obtain the radiation pattern.
Multiplication. Pattern multiplication. Okay, so see here what is meant by this pattern multiplication. For example, if you take two antennas or three antennas or n number of elements, what is the expression to calculate the ET? It is equal to sine n psi by 2 by sine psi by 2. How will you draw the radiation pattern? You take the psi is equal to beta d cos theta minus 1. You will vary the value of theta and you will draw the radiation pattern. Okay. So by substituting different values and changing all these values, it will take so much of time. It will take so much of time. Okay. Instead of this, we are going for a simple technique called pattern multiplication. We are going for pattern multiplication. So this technique is only applicable for identical sources. Okay. This technique is applicable for only for identical sources. So okay. So see here. The principle of pattern multiplication states that the radiation pattern of an array, the radiation pattern of an array of antenna is the product of pattern of individual antennas with the array pattern of isotropic point sources, each located at the phase center of individual source. Okay. So the array pattern is a function of the location of the antenna in the array and their relative complex excitation amplitudes. Okay. The phase center of the array is the reference point for the total pattern. So what is the advantage? It helps to sketch the radiation pattern of any array antennas rapidly from the simple product of elements. Instead of doing all that mathematical calculations, what I have told. Okay, instead of doing all this mathematicals. Okay, so this pattern multiplication, by using this, you can easily draw the radiation pattern. Okay, so what is the disadvantage? The principle is only applicable to array containing of only identical. So this is suitable for only for identical elements. Okay, if the elements are not identical, then we cannot go for pattern multiplication. Okay, so only for similar sources. Okay, so the total phase pattern is the addition of phase pattern of individual sources and that of array of isotropic point sources. Okay, so see here the result pattern of any array of non-isotropic identical radiators can be given as is equal to f of theta comma phi into small f into f. This one, where f of small f is the element field pattern, capital F P is element phase pattern, capital F theta is array pattern of isotropic, and f p theta comma is phase pattern of array of isotropic elements. The angle theta and phi representatively the polar and azimuthal angles. Okay, so this can be easy to understanding by doing one example. Let us go do one or two examples. Okay, now let us see the first example. Okay, now let us see the first example one. Consider here how many elements are there? 4 elements. Now we are going to consider 4 elements. So see here this is the, let us consider first element, second element, third element, fourth element. Element 1, 2, 3, 4. Let us consider all the elements are separated by a distance of lambda by 2. All the elements are separated by a distance of lambda by 2. Okay. So here 1 and 2 are separated by a distance of lambda by 2 and 3 and 4 are separated by a distance of lambda by 2. Instead of this, I am keeping this 1 and 2 as one point A, this 3 and 4 as one point B. Now what is the distance from here to here? Here it is from here to here it is lambda by 2. From here to here it is lambda by 4. From here to here it is lambda by 4. Lambda by 4 plus lambda by 2 plus lambda by 4. What is the total distance? The total distance is lambda. Okay, so here total how many elements are there? 4 elements are there. Okay, so instead of 1 and 2, I have replaced with A, and 3 and 4 I have replaced with B. Okay, so the total separation distance is lambda. Okay, so here 1, 2, 3, 4 all are separated by a distance of lambda by 2. Okay, so elements 1 and 2 are considered as 1 and 3 and 4 as considered as 1 unit. Since the elements are identical, both units have same radiation pattern. Okay, so means nothing but here 1 and 2, you are combining here. What are the things you want to remember is 1 and 2 are separated by a distance of lambda by 2. And similarly, 3 and 4 are separated by a distance of lambda by 2, which are similar elements. Now I am replacing, or I am considering 1 and 2 as point A, and I am considering 3 and 4 as point B. So A and B are separated by a distance of lambda. Here two things you want to remember. 1 and 2 and 3 and 4 are separated by a distance of lambda by 2. A and B are separated by a distance of lambda. If we multiply the radiation pattern of two elements separated by lambda by 2 and two elements separated by lambda, which gives the pattern multiplication, Okay, now let us see here. So this radiation is nothing but from the expressions we can get that this is due to two isotropic antennas separated by lambda by 2. In our example, element 1 and 2 are separated by lambda by 2, and similarly 3 and 4 are separated by a distance of lambda by 2. So this is the radiation pattern for two isotropic elements separated by a distance of lambda by 2. And similarly, we have considered 1 and 2 as A and 3 and 4 as B. Okay. So this is the pattern of two isotropic antennas separated by now A and B. What is the separation distance between A and B? The separation distance between A and B is lambda. Okay. So this is for two elements separated by lambda by 2. This is for the two element sources separated by lambda. Two elements separated by lambda. Okay, now in order to get the total radiation pattern, I want to simply multiply. This is the radiation 2 pattern. The resultation pattern is obtained by simply product of the pattern lambda by 2 spacing of 1 and 2 elements and 3 and 4 elements, and a group pattern with lambda spacing. So multiplying with lambda by 2 and spacing with lambda. How will you get this one? Okay. Whenever for in this diagram you are having major radiation in this direction, here major radiation in direction. Whenever we are both sides are having major loops, okay, we'll get the major loop. In the direction we will get the major loops. Okay, but if you observe in this direction, okay, here you are having null, here you are having major loop. So when null and major loop is there, you don't get any wave. Okay, so here maximum radiation, here maximum radiation means in the direction only you will get the maximum radiation. So this is the total resultant pattern of four isotropic antennas element separated by lambda by 2. So this is very simple without doing the all calculations, simply by multiplying. Okay, we can obtain the total resultant field. Okay, so it is clear. Here maximum radiation, here in this direction maximum radiation. When we do product, you will get here maximum radiation. In this direction, no null is there. Okay, in this direction null is there. In this direction maximum radiation is there. So multiplication it will leads to no sigma. Okay, so this is the final equivalent resultant pattern of four isotropic antennas spaced at lambda by 2. Okay, so this is example 1. Okay, now let us go to the example 2, very, very important one. So it is for 8 elements separated by lambda by. So first element, second element, third element, fourth element, fifth element, sixth element, seventh element. All are separated by a distance of lambda by 2. Okay, so here what I am doing, in the previous case, I have considered 1 and 2 element as A and 3 and 4 as B. Here I am considering 1, 2, 3, 4 as A and 5, 6, 7, 8 as B. Here what is the separation distance? Here the separation distance is 2 lambda. In the previous case, the separation distance is lambda. Here the separation distance is 2 lambda. Okay, now what should we want to do? Okay, we want to multiply that lambda distance with unit group 2 lambda distance. Lambda distance with unit group 2 lambda. Already you know the direction for lambda group. Okay, so this is for lambda group and this is for 2 lambda group. Here also, in this direction I am getting maximum radiation. In this direction I am getting maximum radiation. Whenever there is maximum radiation, the maximum product, in that we will get maximum radiation. Here null is there, here maximum. So cancel takes place. So no radiation will takes place. Okay, so this is the radiation pattern of 8 elements separated by a lambda by 2. So instead of doing all the calculations, we can directly obtain the radiation. We can directly obtain the radiation pattern. This is the this is the goodness in the pattern multiplication. Okay, so we have done 2 examples, one for 4 element array, the other for 8 element array, other for 8 element array. Okay, so this is regarding